Workshop number 2, 1A. So it's a two-step reaction. The first step is going to involve BH3. The second step, it involves NaOH and hydrogen peroxide H2O2. Okay, first thing we're going to do, we're going to number the alkene carbons at least. We're going to number them 1 and 2. So we can obviously look at 1 and 2 and say they're different. Carbon 1 is bonded to 2 carbons. Carbon 2 is only bonded to 1, right? So the other thing we always like to do usually is to draw in any and all H's on the alkenes as well. Okay, so they're different. One's more substituted than the other. That's the first thing to notice. Next thing you're gonna need to know how to do, can you draw BH3? It's Lewis structure. So you need to recognize boron is in the third period. So it has 3 valence electrons, so it can make 3 bonds. But that means that it's gonna it's not gonna have a full octet. It's gonna have no charge but have a full octet. So it's gonna be sp2 hybridized. So you gotta be able to see boron BH3 and immediately draw this. Right? Gotta see it and draw that. Know there's an empty p orbital. Since we're using an alkene, right? These are all these addition reactions. One thing they have in common, for sure, the pi bond is the nucleophile. So we can go ahead and draw in the 2 electrons in this pi bond right there. Now this is not a carbocation by any means, right? The boron's not. This is not a carbocation, but it's still an empty p orbital. So it's still a place where electrons would go. That's still an electrophile because of that. So the first step is the pi bond, right, is going to go into the empty p orbital. Now I'm not done with the first step. That's just the first movement of electrons. Now you also notice at this point, I haven't decided, right? I'm forming a new bond between one of these carbons and this boron. I haven't decided which one it is yet. So I need to think about which one of these 2 carbons the boron's going to end up on. We've already decided carbon 1 is more substituted than carbon 2. So if we think about this, one of the things we need to think about, the boron here, the steric argument is the boron, it'd be easier for the boron to be on a carbon that's less substituted. So the boron's going to go on the carbon that's less substituted because of sterics. So if that's the case, these electrons moving are going to make a sigma bond between the boron and carbon 2, because that's the less substituted carbon. So that's what this movement of electrons is representing, a new sigma bond being formed between the carbon 2 and the boron. Those are 2 electrons in a bond. At the same exact time, the H is also moving, and it's going to be bonded to carbon 1, the more substituted carbon. That's happening all at the same time in one concerted step. So the regiochemistry, the boron goes to the less substituted carbon. That's the regiochemistry. Right? Which region of this alkene is the boron going to go to? Right? We're thinking about the regiochemistry. So this is Regio Selective. It's going to select for one region over the other. So that's the Regio Selective part. There's also a stereoselective part. What's the stereoselective part? If you notice, as this adds, it's all happening at once, it's all going to happen from one side or the other. Because this is an alkene, these are both sp2 hybridized carbons, which means they're planar, which means there's this boron could come from the bottom or it could come from the top. Right? So both things are possible, but it's going to be a syn addition where the H and the boron are on the same side. So I'm going to draw one version of that now, what that could look like. So here's the boron, BH2. There's the H that added. See how they're both on the same side? The wedges and hatches. So this is where we need to be able to look at this and say, okay, these 2 methyl groups were on the same side. So they're going to be on the same side here. There's a methyl, there's a methyl. This methyl and that H are on the same side on carbon 2. So I need to draw in an H here. This is carbon 1 and carbon 2. Regioselective because the boron always goes to the less substituted carbon. Stereoselective because you always get a syn addition. You'd also get the other version of this. And I don't need to change the wedges and hatches at all. And you'd get that as well. Carbon 1, carbon 2. That's just showing that you realize the boron could come from the top or the bottom. That's the finishing. That's when you're done with step 1. Now, the other thing you could think about, they talk about this in the book, the boron has 3 hydrogens on it. So how many hydrogens can it deliver? 3. So every boron, every BH3 could do this exact same thing 3 times. But it gets pretty messy when you start adding another alkene or another carbon piece to here and here, right? But just so you realize, there's 3 H's, so it could do this 3 times. Once we're done with step 1, all we gotta do for step 2 is just replace wherever the boron was at, replace it with an OH. That's it. So step 2, which involved the NaOH and the H2O2. Just draw it exactly as you had it before. I'm just going to draw one of them. Wherever the boron was, now there's an OH. And that's one of our products. And then you could say plus. In this case, is it an enantiomer? It is an enantiomer, right? You do have an asymmetric center. Carbon, which carbon has 2 things bonded to it? Carbon, or 4 different things bonded to it? Carbon 1 or carbon 2? Carbon 2, right? sp3 hybrides and 4 different things. So we do make a mixture and enantiomer here. Just make both. So you have both the regio selectivity, less up boron goes less substituted carbon, the stereo selectivity because it's syn, but you're actually making both. Right? So you actually get the enantiomer, which would of course be, if you have both enantiomers, there's no preference here, you get a racemic mixture. So to see more information on this, you could look at figure 12.35 in Top Hat. It shows a nice picture of this, talking about this regio selectivity, why the boron wants to go to the less substituted carbon because of the steric interactions, and why we always get this anti-Markovnikov product. So check out 12.35, that anti-Markovnikov product, where the thing ends up, wherever we're adding, the important thing, not just the hydrogen, ends up in the less substituted carbon. Another good kind of question is worrying about wedges and hatches and what needs to be wedged, what needs to be hatched. It doesn't matter, it matters what's wedged and hatched, but the key here is when you start with this alkene started with this methyl and this methyl on the same side. So whatever you do, when it goes from sp2 to sp3, these 2 methyls need to be either both wedged or both hatched because they started out that way in the alkene. This methyl and that H, right, I have them both hatched. They have to be on the same side. That's the key part. It doesn't matter what's wedged and hatched as long as you make sure that this methyl and that H are both the same, whether it's wedged or hatched, and then same with these 2 as well. Let's work on naming. So let's see if we can name this alkene we just used in the last problem. So we need to find the longest parent chain with the alkene in it. So the longest parent chain with the alkene in it would be a butene, right? It'd be 1, 2, 3, 4. The question is, we have one substituent, we have a methyl. So we have a methyl. We need to decide which way to number this. So the best way to number it, I think, would be to number it 1, 2, 3, 4 from left to right, not right to left, because that way we have the lowest number possible for our substituent. So the answer to this would be 2-methyl, 2-butene. That would be how you would name this. All right, a reaction with HCl and an alkene. So this is classic addition reactions, but we should look and see here. Let's number at least the carbons of the alkene, 1 and 2. So again, we look at these alkene and say, carbon 1 has 2 hydrogens bonded to it. We should go ahead and draw those in as well. Draw on this hydrogen, draw on the hydrogens on the alkenes. Make sure it's easier to see. We also can see here probably, right, so carbon 1 has no other carbons bonded to it. Carbon 2 has 1. So there's a difference in this alkene. One's monosubstituted, one's not substituted at all, any other carbons. So what we're going to do here in the first step, of course, is we're going to use the pi bond as a nucleophile, and it's go for the best electrophile, which would be the H plus from the HCl. So we'll break that HCl bond. But at this point, we have a choice. Where do we want to make the new CH bond? The new CH bond needs to go on carbon 1 or carbon 2? The CH bond. So the way to think about it, where would you rather have a carbocation? Carbon 1 or carbon 2? 2. So where's the CH bond going to go then? No, the CH bond's going to go on 1 because 2 is not going to get a bond, right? So that, right, be thinking, right, there's two things going on here. You're forming a carbocation, but you're also forming a new sigma bond, right? 2 electrons, a new sigma bond between carbon 1 and this H. So don't forget about that too. Okay, so we're going to make a carbocation. And we made a new sigma bond, CH bond. This H is still there. Number of my carbons, carbon 1, carbon 2. So what new bond do we form? A new sigma CH bond. Let's not forget that. This CH bond is still there. Nothing changed. Have a carbocation. What kind of carbocation is this? It's a secondary carbocation. Very good. Is that the best carbocation we can make? No, so we should be thinking about rearrangements. And what do we think about when we think about rearrangements? We look for those hyperconjugation buddies, right? Those sigma bonds. How many bonds away? 2 bonds away. 1, 2, right? 1, 2, 1, 2, 1, 2, 1, 2. And then what else is here on this carbon that's not drawn in? There's a hydrogen there. That could be important. If I move that hydrogen, if I rearrange, I can make a new plus charge on that carbon, which would make a tertiary carbocation, which of course is more stable, so that's possible. And that's what I'm going to do. New H is there. Plus charge is here. Excellent. This was carbon 1, carbon 2. Of course, we forgot all the way through along for the ride was Cl minus, wasn't it? To balance our charge. Right? We start out with how much charge? No charge. So we make a carbocation, make a plus charge. We better have a minus charge there as well. Now our Cl minus is going to work. So what's it going to do? Carbocation's flat. The Cl minus is going to come in an SN1 type fashion. Now be careful here. What kind of products are we going to make? Let's take a look. We're not sure to start. Chlorine added there. What kind of, so that's do we make an asymmetric center? Do we make is there an sp3 hybridized atom with 4 different things bonded to it? Methyl, ethyl, nope, it's not. Be careful, right? This is not an asymmetric center. Do we need to say plus an enantiomer? No, as a matter of fact, if you said plus an enantiomer, that tells me you don't know what an asymmetric center is. So be careful, right? Always thinking plus an enantiomer. I see a carbocation plus an, nope, no, be careful. Wait to worry about that enantiomers, diastereomers stuff till the very, very end when you're done. Right? So there would be the product. Following rearrangement. So that's the one of the things you got to be careful when you do HCl, HBr, HI. Those make carbocations, H2SO4. If you make carbocations, you can rearrange. Right? The new ones we learned, the mercury, the boron, the Br2, they don't make carbocations, so they don't rearrange. A little more complicated one now. We're going to have the same type of situation. You have an alkene, you have HBr. So we know we're going to make a carbocation. You should be able to see these reagents and say, this is a carbocation situation. It's also regio selective, right? It's regio selective because we're going to pick between carbon 1 and carbon 2. Right? Carbon 2 is more substitutes, so that'd be a better place to have our carbocation. But we always want to make sure we follow our things. Let's draw on the hydrogens. Let's not lose hydrogens or lose carbons. And this one, I'm going to take it a step further and number everything. 2, 4, 5, 6. First step in all these reactions is the pi bond is the nucleophile. It attacks the electrophile hydrogen, breaking the HBr bond. Where are we going to form a new carbon-hydrogen sigma bond? Which carbon is going to get the new bond?
1.
Carbon 1. Very good. It means the plus charge is going to be on carbon 2. But the new sigma CH bond is on 1. This H is still on carbon 2. 1, 2, 3, 4, 5, 6. So we have a secondary carbocation. We should, if that's not the most stable carbocation in the world, Can we make it rearrange to make it more stable? Also, let's not just think about the carbocation, let's think as the molecule as a whole. Somebody should be looking at this being like, that's a square. Squares have 90-degree bond angles. I hope that's what you're thinking. What's the hybridization state of all the atoms in the square? sp3. There's no pi bonds. sp3. What's the bond angle for an sp3 hybridized atom? 109.5. Certainly not 90. So these are going to be strained. Right? These bonds are going to be strained. This is going to be, right, these bonds aren't as strong, right? The orbitals aren't overlapping that well because of the angle strain. So because of that, we're going to want to break this ring open. So what you're going to need to do, right, is think about those hyperconjugation buddies. Now, it's not that wild. Here's the carbon. That's carbocations. We're going to look for what? Sigma bonds 2 bonds away. 1, 2. 1, 2, 1, 2. So now be careful here. One thing we can get tripped up on, there's an H here, right? So somebody might say, well, wait a second. Let's do a hydride shift. Let's rearrange this H and move it over. We'll make a tertiary carbocation. Whoa, you just made it worse. Let's look at why that's going to be worse. So this is, I'm going to draw something that's incorrect now. Hold on to your seats. I'm going to say the blue is bad. So let's say I did that. Let's prove it to ourselves why that's bad. Don't take my word for it. Make me prove it to you. Now there's a plus charge here. Drawing our H's. We didn't lose those H's in that original go-round. Get a new H here. Number those carbons. 1, 2, 3, 4, 5, 6. Okay. Tertiary carbocation. Fantastic, right? Why is this not fantastic? Why is this? Yes, it is a tertiary carbocation, but this is bad. It's bad. Why is it bad? What's the hybridization state for a carbocation? sp2. What are the bond angles for an sp2 hybridized carbon? Bond angles for sp2 hybridized is planar, and those are the 120. Huh. Here it was 109.5, which was bad. Now it's 120. I would argue that would be worse. So this is not downhill, right? This is a tertiary carbocation, but oh man, super duper bad. Right? You can't. It's not so easy. You can't just say, "Oh, all tertiary carbocations work." Right? You got to think about it a little bit more. Think about that hybridization state and those bond angles. Right? All that stuff still matters. So we're not going to do that. So I'm going to redraw this whole thing. All right. So I redrew our original carbocation. So we're not going to do a hydride shift. We're not going to do this from 3. Instead, we're going to look at a different hyperconjugation buddy. These sigma bonds, 1, 2 bonds away. So what are we going to do? We're actually going to break this bond between 3 and 6. And that bond's going to break, and now 6 is going to be bonded to 2. So who has the plus charge now? Where's the plus charge going to end up? Who lost a bond? 6 gained a bond. 6 is now bonded to 2. 3 lost a bond. So it's weird because right here, 3 again is going to have the plus charge, but it's going to look much different. Now we've opened this ring up, right? We no longer have a 4-membered ring. Now we have a 1, 2, 3, 4, 5-membered ring. Much more reasonable. So let's draw that. We can draw it. I'll draw it ugly. Who cares? We'll fix it later. It's okay. It's going to be okay. 1, 2, 3, 4, 5, 6. And where was the plus charge again? On 3. Good. Let's redraw as a 5-member ring. Let's make it a little prettier. This is why numbering is nice, because we don't have to worry. Right? We'll just number. So there's 1, there's 2, 3, 4, 5, 6. And where was the plus charge? 3. Awesome. Are we done? No. So what kind of carbocation is this? Secondary. Somebody might say, well, wait a second. This was a secondary. It was a secondary, you're right. But it was a secondary carbocation with a 4-membered ring, also in the molecule. This is a secondary carbocation without that four-member ring, without that strain. So this is a lower in energy intermediate in this reaction. So you'd be still going downhill, even though you're going from secondary to secondary. So you still got to think about it, right? It's not so easy just to say, right, just like before, tertiaries are always better. No, got to think about it. You can't, like I said before, usually you don't do lateral moves. Well, this isn't a lateral move. It's a secondary carbocation and a secondary carbocation, but there's other stuff in this molecule that makes this higher in energy. All right, so now we have a secondary, and so again, we need to look at, can we make this more stable? So we have to look for our hyperconjugation buddies again, and we actually, of course, can. There's an H on carbon 2, and if we move those electrons to 3, we can get a tertiary carbocation now again. So what's that look like? Get that plus charge there. 1, 2, 3, 4, 5, 6. And of course, all along the way, we've forgotten him. Br minus has always been with us to balance our charge. So now it finally matters. Now we can do that between two molecules reaction. And of course, it's going to get, it can attack from the top or the bottom, but is that going to matter here? Are we going to make an asymmetric center here? Take a look. Are we making an asymmetric center? Is carbon 2 an asymmetric center? Does it bond to 4 different things? It is not. Right? Methyl and bromine are different, but then 3 and 6 are the same, right? It becomes symmetrical. So you don't need right plus an enantiomer. As a matter of fact, you don't want to write plus an enantiomer. This is the only product.